In this episode, Sam and I will talk about the challenges of taking a vision of chiplets, how you break up semiconductors into components that you can put together in novel ways and defy the slowing of Moore's Law and making it a market reality. I'm joined today by Sam Nossinger. 35 years in the industry, he's an AMD Senior Vice President, Corporate Fellow, and leads Product Technology Architecture. Sam was an innovator, driving many of the elements of not only power efficiency across the portfolio, but leading the charge on chiplet architecture in the company. Sam has, over 150 patents?
Yeah.
That's fantastic.
No, I always, patents for their own sake are really of little value. I care about the ones that actually changed the industry and transformed our products to make it more competitive.
You know, it was such a pleasure for me to have the opportunity to work with you for over a dozen years. And as I came to AMD in the CTO role, one of the things that attracted me was the daunting challenges we had in the industry. And I knew that we need, kind of a chiplet type approach, and AMD had great IP, but the question was how to really, define the technology, architect the technology such that you could leverage chiplets and really bring it to bear across a diverse and complex technology portfolio. It'd be great to just share with our audience how you thought about that from an architecture standpoint, and some else call it the base fundamentals that would have been blockers for anybody to be able to take that on, and some of what became actually key enablers for AMD to be a leader in deploying chiplets.
Yeah. Well, I think you could see the reason you joined AMD is because you saw the elements of success, all of the pieces there, but they just weren't put together in the right way. And the Infinity Fabric approach was essential for the challenges of the future, right? Because we could all see Moore's Law's days were numbered, right? And we weren't going to be able to continue doing things the way we did before. And the challenge in our industry, there's always somebody on the leading edge, but when someone jumps too soon to a new approach, a new technology, it falls flat, and the ones who do the evolutionary good enough approach end up ahead, right? So the challenge is knowing when to make the leap to something new, and that's what AMD's always been really good at. We are a very data-driven culture, very engineering excellence in our DNA, and I remember actually before you came, Mark, I was leading investigations of disaggregating our SoCs. Now, we ran into a number of problems. One, the technology wasn't expensive enough and to justify it.
We didn't hit the crossover point yet.
We hadn't hit the crossover point, and also our SoC architecture really wasn't chiplet friendly. So we'd evaluate it and drop it and do things traditionally, right? And of course, then you joined, and you had that vision for where the future was going beyond just our next-gen product. We were a very tactical company trying to survive at the time. Beyond that, and you got the teams to develop the more modular architecture, which was a critical enabler.
I would like to just spend a minute on modular architecture, because I think everyone takes it for granted now. And we'll talk about, I'd love to get in later and get your thoughts on some of the standards and how this is becoming much more prolific in the industry. But at the time, it was actually radical thinking. And I remember, that we pulled all the engineers together. I remember distinctly, it was February of 2012. We had the fellows conclave, so all the technical leadership were together.
Yeah, that's right.
And we had, a candid discussion that if we didn't change to, what became the Infinity Fabric approach, a common way across the company to bring the IP blocks together, that we couldn't compete. We had opinions that thought absolutely that was the right way to go. We had different opinions but in the end, we came together. I'd love to hear, how you and the technical leadership, your peers, how did you swing the the tide of thought along
Yeah.
the way of this modular approach?
These sorts of things, they're highly debatable, and people can come down on either side, and so it boils down to their emotional attachment to an approach. And we had a lot of that. Engineers, they invest years of their lives. Maybe they made their career on a certain approach, and now you're telling them their baby's ugly and we need to get a new one, right? And that's hard to get people over that hurdle. And so once again, with the data-driven approach, we had to look at the rat's nest of signals and all the complexity and what it took to verify these designs, and the fact that we were going to need to be building more SoCs. We weren't even talking about chiplets at that time, but we knew we needed to have a lower barrier to designing new and diversified SoCs to meet the market requirements. And so that was the data we brought out. Some people agreed. Some people felt that they could tune up the existing approach and it'd be good enough and less change. And so we had to rally the team. And as a leader, when you exude enthusiasm and confidence in a change like this, it makes all the difference, right? And so we had a core team of leaders, and actually it's very similar in composition to what we have today. Most of the same folks there, and we all realized this is where we needed to go, and so we rallied the support, got the data, and we had a lot of meetings. They were controversial, and some people, it was more change than they wanted to deal with, and they went their own way, but we made the change, and it was transformative.
And I think there's a backdrop that we can't discount, and that is, if we didn't change, if we said, nothing changes, we can just evolve with historic approaches, I think people accepted that the path that we were on would not turn around the company. It wouldn't allow us, just as you said, to diversify markets. I mean, AMD at the time was mostly all PC revenue, and the way to grow was to really expand in gaming and to really grow in the data center and be able to proliferate that IP, which all hinged upon that alignment on a new approach that you just described.
It did, and the magnitude of the new opportunities became apparent a couple years later, right, as we started to work on what we called Zeppelin at the time, which became our Naples server platform.
First generation EPYC.
First
server.
generation EPYC. And if it weren't for the Infinity Fabric innovations and the well-defined modular lightweight interfaces that came out of that, there was no way we could have split the design up into multiple chips.
It was actually a pivotal decision to take that first generation of x86 Zen-based server and to split it out into a modular approach of chiplets that could then be tied together by that Infinity Fabric. And I recall the huge debate that said, we're going to absolutely fail. Why? You cannot split that out and have a fabric that could still allow you to hit the performance goals. That simply the mesh between those chips would add too much latency. It would be too much power. The protocols couldn't support it and still have quality of service for the most demanding data center workloads. And I remember just pitched debates. But I go back to what you said earlier, data. Data talks. And then data talking means that you have a culture that listens to data. And I remember, sitting down with you, and I remember when we took it, we took the proposal up to Lisa, it was the data that won the day, and we landed on that modular approach. Yeah. And I think the rest is history. It's grown tremendous market share.
Yeah, and it wasn't, the challenging thing with these changes is data is a function of the team's ability to execute, to hit the goals. The latency was too high. The power cost was too high. But we had a team of can-do engineers who said, I know how to solve that problem. And so I will deliver a lightweight interface, and I will slim this down. I will eliminate cycles of latency. And if we hit these targets, now we have a multi-die solution that behaves just like a monolithic SoC. And so we set those targets, and then we oversaw the team's execution to make it happen. And it was so transformative, Mark, just that first one with the Naples design, because we were a very lean company. We didn't have enough engineers to do multiple chips. We were trying to compete against a competitor who had resources for 5 different SoCs in the same space. We could afford one. We could design one chip.
That's right.
And so we did it in the most flexible, modular way possible, and out of that one chip, we got 5 products. We had the single die solution, we had the 2-die solution, we had the 4-die solution, we had variants on each of those. And because of the lightweight interfaces and that we delivered on the engineering challenge, and we got the bright minds in the company, it was a winner, and it set the stage.
I don't think the industry understood exactly that aspect of the flexibility across a portfolio that it gave us. And I remember some of our competitors deriding us at the time with that first generation of EPYC server that, hey, you're gluing together a bunch of chiplets here, a bunch of chiclets, I think was the phrase. And I was actually proud when I read that. It's like, yes, that's exactly what we're doing, and we're going to do more of it going forward.
Yeah, I know. You don't hear competitions singing that tune anymore, right? They're trying to replicate the chiplet approach, but you know, that's the great thing. We picked the right time in the technology development to make this big change. Like I mentioned, you go too early, you're going to get overstepped, and if you go too late, you miss the boat, right? So what we call the Rome generation, second gen EPYC, that was really the foundation of the modern chiplet era, where we've got specialization of chiplets in different technologies appropriate to their function. And we can have, you know, multiple, you know, we can scale performance with chiplet count, we scale power with chiplet count. We have a cost optimized, highly flexible platform that is completely unachievable with a traditional SoC design. That's where it's not like we just got cheaper silicon and it's a bit more performant. We are accomplishing things with chiplets that legacy design approaches simply can't achieve. More cores, more I/O, all the features that customers care about.
Sam, you know, I go back to that theme yet again, that we're data driven, and you know, you in your role were a data generator and an algorithm generator to figure out, you know, how do we make those trade-offs. Yes, with the EPYC server roadmap that we talk about, but really across the portfolio to AMD. I think people would be really interested into the thinking that goes in. It's a lot of trade-offs. So how do you think about that and in terms of die area trade-offs, and as you said, even technology node selection?
Yeah, no, it's a complex equation, and that's you know, there's the baseline packaging technology, there's the silicon itself, and then there's how the architecture can partition. And then intersecting all of that are the market requirements. So there's no simple formula, right? You know, you can run the yield equations and you say, okay, if I pay some overhead to connect these chiplets and it adds 10% die area, then a 200 millimeters squared starting monolithic SoC is kind of the break even, where if I cut it in half, it's better economically, right? But that's not actually good enough because it takes more effort. It's harder to test, assemble. You know, the chiplet may not be the right solution. Where chiplets really excel and shine is when you need performance versus cost scalability, and you want to hit a broad market with a smaller set of silicon components. And that's what we did with Rome and with our Ryzen line, with the chip, and the leverage we get across those. So the multiplicative factor of a chiplet design, where it anticipates the different usages of the chiplets and different counts and mixing, and like with the desktop application of our server CPU chiplets, we designed a new IOD because the I/O requirements for desktop and PCs are different.
So same CPU, but unique I/O chiplets to handle the unique market
unique I/O
requirements.
chiplet. And you know, that's actually not a big cost, development cost, because A, it's about 1/4 of the server chiplet, simple design effort, and it's a legacy N-2 node technology, so a lot less expensive to manufacture and tape it out. And that's the beauty of chiplets. You know, instead of doing a big, expensive, leading-edge technology for each product segment, we can design a chiplet that can scale up and down, and then minor derivatives can cover entirely new markets.
That brings us sort of where we are in the industry. People are adopting chiplets. There are standards coming to bear. I would love to hear some of your thoughts maybe on UCIe and just some of the standards and how that could play out.
Yeah, no, obviously that's where the industry needs to go, because the expense of developing and manufacturing leading edge technology node products extremely high, and yet the market need for customization is far greater than it's ever been, right? So you've got this big barrier to entry, and then you've got this demand that needs specialization, because domain specific accelerators, that's the way to have the best perf per watt, perf per dollar. So absolutely essential to progress. Can't afford to do it, a specific product for each one of these domains. So what we can do is have a chiplet ecosystem and library, essentially. And so you can envision, you know, we mentioned the IOD and the CPU chiplets that go around it. If you have an IOD that enables a platform and has the I/O, and then have different chiplets that could be general purpose CPUs, maybe it's an AI accelerator, maybe it's a special network accelerator, a standard interface that gets access to the memory and I/O attached to that central die. And even with UCIe, it opens up the opportunity for third parties to exploit that.
Yeah.
And you know, companies who want to do a custom platform and leverage everything else can just do one little chiplet and bolt it up. So the opportunities are endless. I mean, we're going to see much more of this proliferating in the industry, but it does require standards and carefully thought through design platform capability.
Absolutely. But interconnect is always very, very tough, because you've got you know, scale up and scale out needs, and you've got demanding power and latency. And photonics is out there in networking and Ethernet, but it hasn't come into mainstream compute. But I think about chiplets, and you know, it could be an enabler for other innovations. You know, photonics being an example.
Yeah, no, that's a perfect example. So, you know, we talked about the heterogeneous process technology for Rome, right? And that enabled, you know, a lower cost, more efficient ecosystem, quicker design spins. But even more heterogeneous is if you take in, you know, electrical to optical transceivers and fiber attach. And that all sounds great with legacy approaches, but if you don't have a low power die-to-die interface and high density interconnect, it's not going to be achievable. It's not going to make sense, right? Because if we're using traditional SerDes links at 6 to 8 picojoules per bit, right, there's too much power driving, because optical, you bolt optical on because you want massive bandwidth, right? So you need low energy per bit for that to make sense. And in-package chiplets are the way to get the lowest energy interfaces. So the leverage is direct when the industry is ready to make that leap to co-packaged optics, and it's coming.
It's an exciting future. There's photonics coming. There's new power delivery. There's new memory approaches. I don't think, Sam, we are going to be bored in the coming years.
I could be bored.
And you know, you look at MI300, and it really embodies, Sam, almost all the trade-offs that we talked about. You know, you were integral part in working with our AMD Instinct team in those trade-offs, and you know, both a 2.5D lateral combination and a 3D stacking combination to pull off what is now world-beating inferencing and competitive training for AI, the most demanding AI applications, and has brought competition to the data center GPU market.
Yeah, I couldn't agree more that we're at the cusp of the most exciting era that in my long career, and yours I'm sure as well, we've ever been a part of. And in MI300, necessity is the mother of invention, right? And we had all of those competing demands. We had a set of tools to work with to meet those demands in HPC, AI, and the components that our teams had developed. And it wasn't like we just leapt into 3D sight unseen. We had had a very long development timeline that culminated in the Vcache in our Ryzen and EPYC products, which provides great performance amplification, but it's optional. We don't bet the product on it. And that had been in production a couple of years, but with MI300, we realized within the constraints, in order to have a world-leading product, we needed to bet the farm on achieving a 3D stacked integration, which is really the epitome of modular chiplet architecture. And we're extremely proud of that engineering achievement. I mean, it's really a marvel of integration. And it combines not only Instinct-specific chiplets, but the other great thing, in order to have that revolutionary integrated, what we call an APU, an accelerated processing unit for high-performance computing, where the CPU server, which is traditionally a separate host processor, is integrated directly in the GPU. Well, we had the CPUs and we had the GPU. How do you put them together? And that's where the great engineering culture of AMD comes into play. You know, I spent a lot of time in the CPU teams in my career and continue to know them very well. And so I just went over to, to my buddy Dave Johnson, who develops the CPU chiplets, and I was like, Dave, we've got to figure out a way to take one of your CPU chiplets and integrate it on the GPU. Is there any way we could do that? And he's under his severe schedule constraints, and he has all of his targets and goals, and it's like, first instinct is, are you kidding me?
Instinct, no pun intended.
Yeah, that's right, no pun. But, in the typical AMD way, he went off and thought about it. And lo and behold, there was like just a couple blank spots on the edge of that chip, and we could put a MUX in and use the same Infinity Fabric interface that we use to connect to the I/O die for the server, and have a 3D version of that next that goes down to our IOD on the Instinct part. And so we're able to use the exact same chiplet, minor upper-level metal mod, for our MI300 as we do for the server parts, and interchange them, and do a no CPU version for the AI market, integrate the CPUs for HPC. It's really been amazing to see that come together, and it's positioned us extremely well for this high growth segment.
It has been amazing to see it come together, and it really emphasizes the point about the necessity for a long-range vision and an architecture, because those are not the kind of decisions that you can do late. You talk about that planning and how do you line up the partitioning of what function goes where, the interconnect, and you have the thermal constraints. You can only 3D stack where you can manage it from a thermal standpoint. I know there's just a myriad of facets that go into it. So I love the example of MI300 in terms of chiplet architecture and the kind of collaboration that it takes across teams to be able to pull that off. And I'm even more excited as to where we're going in our AI and HPC roadmap going forward. We've got great stuff coming down the pipeline.
We have a tremendous set of tools in our kit and the engineering minds to put them together in ways no one else has thought of that will make a huge impact to the market. So yes, very exciting days ahead.
Excellent. Well, Sam, thank you so much for joining today. This is an area you and I are so passionate about. We can come back and do a part 2 and a part 3 down the road because the space is evolving so quickly.
We've just scratched the surface.
Yeah, exactly. Well, thank you. It was so fun talking with Sam about chiplets and AMD's industry-leading modular design approach. I think some of the main takeaways from our discussion are that it's hard. You have to really architect how to create a chiplet approach. You have to create a design system that could support it, but more importantly, you have to bring the engineering culture along with you to drive adoption and to really deploy it across a broad portfolio. Thank you for joining us today on Advanced Insights. I look forward to bringing you more in-depth conversations on cutting-edge technology, industry insights, and visionary perspectives from some of the brightest minds in the field. If you enjoyed today's discussion, don't forget to subscribe to AMD on YouTube and follow me on LinkedIn so that you never miss an episode. Technology is always advancing, and we can't wait to share with you more insights in future episodes.